both of these earlier on, this will just be 1 or 2 marks. Go and do this, go and get the formula. If I was in charge of the module, I'd get rid of it, but I'm not. Okay.
So you just put your signal over your blue.
Yeah. And the formula's in the thing, so it's a nothing really.
Oh, so it's signal over X bar. It's a comma there, you don't need to.
Say again?
In the formula there, you.
Yeah, so this would be if you kind of think you have all the data, that's the population ones,
Yeah.
and they're the sample ones. Now, as I said, I really do want you to get the right one. In the past, I've told students that, oh, if you mix it up, I don't care. Now I'm going to say something else. I'll give you the marks, but I do care. You should understand the difference between them. Okay. Now this is another one. Now this one is probably more important. So we had something like this earlier on. So the income distribution might look something like this. And actually this would be something that I didn't understand, so I made it tested you to understand it wrong like I used to as well. Do you think it's kind of falling to the left or falling to the right?
There's a sharp or dip on the left. If it was
Kind of dipped on the left. Where's the data? Basically, I used to think this went skewed to the left. It looked like the data was pushed to the left somehow. But that's actually kind of wrong. This is where the most of the data is here. This is normal. It'd be more normal for it to come down and make a bell. This stuff is the skew to the right. So in terms of income, like it's normal to be in this area. It's normal to have a shape like this. But millionaires are way over here. They're skewed to the right. Now what actually is skewed is the mean. So if everything was symmetric, so if you had so I'll just kind of put a symmetric thing underneath this. So if everything was symmetric, like a bell shape, the mode and the mean, which is the average, would come at the same place. They coincide. So if it was symmetric, well, this is where the mode is, but the mean would also occur there. So this green thing is supposed to represent if there was no skewing, if everything was around the dominant average, just as likely to be 5,000 higher as 5,000 lower. This is what you get. The mode and the mean will coincide. But what you have here is actually data that's pushed over here, millionaires, and they make the mean bigger. So the one we said the last day was that if you'd one person earning €1 billion extra in a year, it would push all of our mean income up by €500. That's what it means by skewing it. So you normally, when the data isn't skewed, messed around like this, the mean and the mode are in the same place. But when you've got data pushed over here like this, the mean is bigger than the mode. So it's skewed. So this is kind of pushed this way. Now I'm going to use language here. So one of them is skewed to the right. And then there's other language which is positively skewed. So this means the same thing. So this is the same as positively skewed. There's just different terminology for the same thing. And what it means, it just means, to be honest, I preferred skewed to the right. I think it's on the autumn paper. The other lecturer has written the paper and it says, is it positively or negatively skewed? I prefer to say, is it to the right or left? And you just said, well, I've already written it. I said, well, I'll show them both. So positively skewed, it means the same thing, but what it means is this thing is positive. Positively skewed is the same thing as saying that the mean is bigger than the mode. And this coefficient then becomes positive. And
How is the mean bigger than the mode?
so the mode is so if we go back to the income, the mode will be, say, if you put all the incomes in boxes of, say, €100, the mode would be the box that contains most people. So it might be something like, I don't know, 25,000, 23,000, something like that. But the average is when you add up all their incomes and divide by the number of people. But because there's millionaires, the mean is way, way bigger. So it's like the estate where one person makes $1 million, one household, and the rest of the households make 70. The mode is 70, but the mean is way bigger. So that's how they aren't equal. And it's because of what's called skewing, which is where your data over here and not over here. So there's kind of data skewed to the right. Like you could even come up with, situations where if this coefficient was bigger than a certain value, you shouldn't use the mean. It's not representative. If this is too big, you should use something like the median, which will say, well, half people make more, half people make less. So this is a formula that's also on the table. So you would have calculated the mean and the standard deviation first, and maybe the mode, and then you just bang it in. Maybe just one mark or two. These formulas, the coefficient of variation and skewness, are on the exam paper.
Is the median half of mode and mean, is it?
No.
No.
No. Median is the value that half the data is bigger, half the data is smaller, which doesn't have to be the same as that. Okay. So we'll have a look at some examples. So if you look at the numbers look really annoying. You see the 1.45 and all that. Now, if you look at the old exam paper, say on the back, go to the back, there should be an exam paper there. So it's actually on a certain page 158. Oh no, sure, no, can't see it there. Basically, I had a disagreement with the other lecturer, and I actually won this one. He used to put them like, so you might see this in the old one. So rather than saying 0 to 10, 10 to 20, 20 to 30, he was using a reference that would go from 0.5 to 9.5, and then 10.5 to 19.5. And I just said, see how that's better than that? How that's better? Alright, so some of the older papers are kind of written like this. Well, to be honest, all of them. I edited that one in your things. So I kind of had the argument with him. I said, no, we do it this way. And I actually won that one. So these are old numbers and they just look a bit funny. It'll be more typical now. You'll see maybe it's like 0 to 10, 10 to 20, 20 to 30. Here it might be something like 1 to 1.3, 1.3 to 1.6. The numbers will be nicer, is what I'm telling you. Okay. So this was 1.2 to 1.4, 1.5 to 1.7, and these bits were left out, which I wasn't happy with. Okay. So the histogram is absolutely simple. So it's F versus X. Now, actually, you can have things where the bins are different widths, and it's a bit more difficult, but we're just giving you equal widths, so it's very straightforward. So now, again, in the question that you get, the numbers will make more sense. So I don't know, I'll be giving you like 0 to 1, 1 to 2, 2 to 3, or maybe like this. But what you'll be able to do is on the graph paper, pick a scale and off you go. So this one, there's not quite a scale there. These numbers are ridiculous. You wouldn't do, you have stuff like, for this, I don't know, 1 to 1.5, 1.5 to 2, 2 to 2.5. You can make a nice scale. So these are kind of nasty numbers. But it's pretty much a bar chart once you've set up your scale. So 1.15 to 1.45, there's 8. Let's just go up to 8. There we go. Up to 15. Up to 24. Obviously this is easier on graph paper. Up to 29. 19, 4, and 1. So this is your histogram, F versus X. So now there's a question, calculate the median and interpret the value. So we're going to give you 2 solutions, and you can do a similar story, you'll be able to do one. So we'll just do the other one here, B part, or one way of doing it. So the median is the value such that half the data is smaller than it, and half the data is bigger than it. So if we find out how many data points there are, first of all, 23, 47, 76, 80, 81, I see 100. Okay, so I'll say n equal to 100. You want to find the 50 smallest ones. So you just count up to 50. So you have 8 in the first, add the 15 the next, so you get up to 24 here. So I might just write down n over 2 is equal to 50. If we go one more, we get 48 of them, because there's 24 in this. And so it's very, very close to 2.05. We just need 2 of these. And there's 29 in there. So if, say, there was only 4 in there, for argument's sake, you would just go halfway across. You go a certain fraction across. So if you do it like this, you can just write it down. Median is equal to, so the 2.05, so it's going to be bigger than that, plus a certain fraction. You want to take 2 out of the 29 of the distance across. What's the distance across? 0.3. So this is approximately equal to rounding. You just want to take 4 significant figures. So I'm getting 2.01. Sorry, 2.071.
Where does 0.3 come from?
The 0.3 is the width across. I'm going to show you that there. So the distance across is 0.3. You want to take a fraction of that. You want to take 2 out of the 29. Now this formula isn't written down. You have to understand what you're doing. If you can't get your head around that, you do the OGIVE.
What's story 48 there again?
48. So we're trying to find the median is the value such that half of them are smaller than. There's 100 data points in total, so we're trying to add up, keep going till we get to 50. And so 50 will be smaller, 50 will be bigger. So we got up to 48 here. 8 plus 15. Shite. That's 47. 47. So we need 3 of these, sorry. So we're trying to add up to 50, so we have 47 under there. Right.
Is it 3 over 29 multiplied by 0.3? Or is
Yeah.
that what that?
Just the 3 over. So you're starting here, and you're adding on a little bit, a certain proportion of that width. So it's just the 0.3.
So
Are you getting something different on the calculator?
probably don't know.
I've got there. Yeah. plus. Okay, so if you don't like that one, this is your other way of doing it. You do this cumulative frequency table. So how much of the data is less than 1 point, maybe I'll just write some other stuff here on the other page. So I got stuff in here, we got 19 in here, we have 4 in here, and 1 in here. Have we got another problem? 76. No, we're okay. Right. So, how much of the data is less than 1.75? 24. Less than 2.05? Less than 2.35?
Should that not be 23 instead of 24 or 15, is it?
Yeah, sorry, that should be 23, is it? But that thankfully doesn't mess us up. So yeah, that should be 23. The 47 is to the right. In here? 76. Then add on 19 more. Get 85. Ah, fuck. Oh, this should be 95, shouldn't it? Oh yeah, that's alright. 95. 99. Okay, it's alright. Had a heavy weekend in Dublin, I'm still not right after it. That's why your tests aren't corrected either. So now you plot this, so you plot f versus less than x. So how many less than 1.15? 0. How many less than 1.45? 8. Obviously your graph paper, this is better. Less than 1.75, we're 23. Something like that. 47. Doing it rough here. 76. Something like that. 95. Something like that. 99. Something like that. 100. Something like that. And then you freehand try these up. Now this should never dip, it's always going bigger and bigger and bigger. Something like that. So we want to find the value such that 50 of them are below, and if you draw it a bit funny, like I probably have done, you don't quite get it. So if you come over here and you do 100 over 2 is 50, and go across from here. Now I'm going to go over this red dot. Not too bad. Come down. This will be the median. Obviously with graph paper and nicer numbers this is easier, and I'm not really going to cheat and write that. I'm going to say 2.1, I don't know, something like that. So you'll see some of the past papers say draw an ogive, and mine one says, I think it says using an ogive or otherwise. So the otherwise is kind of using the histogram and just adding it up and doing that. Otherwise you can go off and do this.
And what question is that for in the final exam?
Question 2.
Question 2.
Yeah. Which question 2 and 4 you'll be advised to do. Yeah. Now there's a little question there underneath it says interpret the value. So the interpretation is half the data is smaller than this, half the data is bigger. So you can say it either way you want. I'd say half the data is less than the median. I don't know what's going on about bottom 25. It should probably say bottom 50. So one more time, the one above, although it kind of seems more accurate, so kind of using a formula, it's assuming that the data is equally spread out on the bin. The ogive with the curviness is kind of taking that out of the picture, but obviously because you're doing it by hand it becomes far less accurate. So theoretically the ogive is more accurate, but in practice that formula is.
Only when the bins are.
If you were to write out that formula,
I would tell you I would tell you to okay.
if you want to write it out, like, because it's 2.05 by 399 there.
Okay, I'll write a formula. No, it's not on the table.